bolts connected in here every 60 degrees.
What's the part?
It's a flywheel for a small engine I'm making. This flywheel is going to be machined out. I'm making spokes here. I'm machining them today. It's almost as easy to make one as it is to make the pattern and go through the process of casting. Chip from kind of balling the pill, and it lubricates the cut so the chip comes out. That's what gives the fine odor of the machine top. It's called sulfur oil.
I don't know how to add the fly on. No, not me.
Different size, right?
Yeah, that first bit was a cylindrical. That's a very stout, rigid drill, so the hole will in fact go where you want it to go. Now this drill is going to pick up that taper so that there'll be less deflection when you come with this drill and want to go where you put the original hole. Once it's established a hole valve, it's going to go pretty much, yeah.
They're hot and come up, aren't they?
It's hot. What I'm doing is indexing work 60 degrees.
So it's going to be 6 holes.
There's going to be 6 holes each space. That's going to create the bottom radius for the spoke. So the machine, you got to remember, I'm machining make everything without the spokes, and this is going to give me the radius. Then later, I'm going to put another bolt circle out here, and then I'm going to connect this with a mill cutter, mill all this way like that. Mill a little triangle out, and then mill another triangle out, and so forth, and then hopefully I'll have 6 spokes equally spaced.
You want to shoot on?
Well, I was thinking of scuttling the cover.
Which one?
One of those. I don't know, I've got sandals on. I watch my feet and my hip and your toes.
Also, it's cool to drill too. That's why you see it's going the get way, but it's also burning off. Burning off the oil and that kind of stuff. Now this is a pretty nice feature that I picked up from my machine during use. Something before known as a digital readout. You know, before you used to read dial here at the micrometer and that would give you the location. Now it's all read out digitally. This is an electronic device that measures a glass scale inside of this. The glass scale has etched in the glass very fine lines, and it counts as it moves along, and it can locate within a half of a thousand.
Wow.
So this would be, I moved over 5/8, which is 625 to the left, and this would be a plus. I went the other way, this would be a minus. This is my X, which is this motion, and Y motion is this way. This would be Z up and down. But it's nice. That is nice. It helps. You see here, you've got to count revolutions and then come back to where you were. If you want to go 5/8, it's 200 revolutions per rotation. So that would be, you would have to give it 3 revolutions plus 25,000 on the dial for 5/8, which actually becomes second nature after you use the machine. Whereas here, there's less room for error. You don't have to worry about, did I count enough? When you're going to move 5 inches, you know, that means you've got to move this, I gotta stop and think, 5 inches, it's 5 turns per inch, so it'd be 5 times 5, you've got to go 25 revolutions plus whatever fractional part of that inch you're moving. And you can make a mistake. Dad always used to say, throw your scale down and measure to make sure that you actually did move that amount. If you forgot 1 turn, you'll be off 200 thousandths, which is, you know, a little over 3/16 of an inch. You can read that on the scale. But that's really, really nice.
You want to see if you can get a shot of the Hargrave?
Of the what?
The
Clock?
Hargrave clock. You step on
Congreve's clock.
Congreve.
Yeah. Stand up on the
Step
stool.
stool there.
I don't know if there's enough light.
So tell us about this clock.
Well, this is a Congreve's clock. It was invented by Sir William Congreves of England in 1808. And this is a replica of that clock. It's a bit bigger. The original one had a 3/8 ball and the table was a bit smaller. And this here one's been redesigned by John Wilding from England, which is a mock-up of the same clock. He chose to make it a little bigger using a 7/16 ball because the clock would suffer from having enough energy in the ball to strike the escapement and to properly release it. So he felt by having a larger ball, 7/16, it would strike this with a little more momentum in order to cause the escapement to advance the clock by 30 seconds. What it does is it takes 30 seconds for the ball to go from this end of the table to this end, at which time it strikes the escapement and it causes the ball to traverse down the table in the opposite direction, there again taking it 30 seconds. Now when it hits the escapement, it advances the clock by 30 seconds, this by half a minute and proportionally the hour. And it's driven by a large spring inside of this drum to a fusee via a cable, and it's an 8-day clock. It runs for 8 days between windings.
Tell us about the materials, too.
It's wound with this key at this point right here. The material is mostly brass. That's my initials.
I know.
Yeah. Well, he put his initials in with a saw, and he saws everything out, which looks fine. But when you turn it around, you can't read it because it's backwards.
Yeah.
So I milled out most everything on either side, and got my initials in there so it reads on either side. I had to put a few of my own touches in, one of them being the key and the ball bearings, which I had several of. Not knowing what to do with them, I mounted them and used them in the clock here. I used them up here, and I used them up here on the second shaft. The original clock, needless to say, didn't have ball bearings because they didn't have ball bearings in 1808.
So does this make your clock more accurate?
No, it doesn't do anything as far as accuracy goes. It's just I needed a place to use them, and I didn't have a place to use them, so I put them in here. See, I'm a collector of a lot of small bearings, as you can see. So these are all used bearings. I don't know if that's going to focus at this point, but I put them in the clock because I had them, and they work well.
Any other?
These are some miniature 8-ball cue balls, and these black ones are 8 balls from the local billiard manufacturing place here in town. And I buffed off where it said 8 on the 8 balls. And these are threaded, and they're the leg adjusters. You rotate the balls on this thread, and you adjust the table so it's perfectly level. Needless to say, it's not going to work unless it's perfectly level. Another thing I put in is a hydro check right back here. I don't know if you can get that with the camera, where I'm pointing with my finger here.
Yes.
There's I had a problem when it would strike the lever. It would bang the table. So what I did was I put a little piston in here in the cylinder, very much like a screen door air check. And what it does is it has to compress the air as it shifts from the bottom to the top, causing the action of the table to be smoother. The time is adjusted via the crank in the rear here, which angles the table a bit steeper either way. So if your clock is running slow, you adjust the table so it's tipped a little more and the ball will run faster. And if it's running too fast, you tip it back so it's not running, so the ball traverses a bit slower. Needless to say, it's not the most accurate timepiece. For $2, you can buy a quartz watch that'll keep much better, more accurate time. But you got to remember, this was designed, let me think, 1808. They hadn't really settled in on the pendulum yet. They were looking for means of keeping track of time, and I'm not even sure if the pendulum was invented at that period. But people were looking for means for keeping track of time, and this was just one of them, rolling ball clock. It was never successful as far as keeping track of time. Probably the best you do is 15 minutes in a week, and that's not really good enough for today's standards, I guess.
Not good enough for the National Bureau of Standards.
No, no. When people come and they look at it, I says, feel free to set your watch. But it's, I had a lady tell me one day, she says, you know, I've heard of alarm clocks that wake you up. She says, you watch this long enough, they'll put you to sleep. But it's, the fact that it's so different, I think, is what makes it unique. I've seen a lot of clocks, and most of the clocks you see today, they have quartz movement, and they put it in a picture, or they make them fancy. But I mean, this here actually works different. The whole principle is different. To time a ball that rolls down a table.
Let's get over here. Is this an engine?
Yeah, it's a miniature steam engine. It's actually was supposed to be much smaller than this, and I scaled it up by 1.5 times. And it was originally designed for a small steamboat. This is a very early marine steam engine. Probably the design dates back to maybe around 1800 in that area. It's a single acting, which is not a very efficient steam engine. But the valving and the piston is all done with the same movement. As the cylinder rocks, it aligns the proper ports in here, which causes the piston to go down. It's, like I say, it's not one of the better designed steam engines. I have some over here that are actually of a better design. This is a mill engine that was designed, very common use, typical mill steam engine that was built, I'm going to say 1880, 1860, and it was used right up till about 1920 in a lot of factories to run everything in the factory.
Could we reposition this over here, maybe? So you want you want to have a seat to get it?
Get it some more?
Yeah, so you can see everything, because when you're on that angle.
Oh.
You can only get so close that you start to lose the focus, I
Yeah.
think, when you get much more than 3 feet.
It's got a macro button, but I don't know what...
I don't know how to use it. I've tried to use that before, and I was never able to. Can you get it? Is it focusing?
Not really.
No? I was never successful, but that doesn't mean it doesn't do it.
Is this a working model?
Yep.
What kind of fuel would you use?
You need a boiler, and you can burn any kind of fuel, and you make steam,
Oh, okay.
and the steam pressure drives the engine. So regardless of how you boil the water, you're going to, have power.
Yeah.
The beauty of it is it didn't require gasoline. You could use coal, wood, any available fuel to make steam, and you had power.
Mm-hmm.
That was the beauty of it.
So if you hooked up, this is where the steam would go?
Yep.
So if you just put some... Mm-hmm.
Are the little arrows going across?
Yep. And it's rolling right in front of me, too. What treasure do you have in there?
This is a replica that I built of a quarter-scale Bentley BR2 rotary aircraft engine. This was the engine used in the Sopwith Camel and the Sopwith Snipe, which is a British World War I fighter plane. You know what I could do? I could put some newspaper down and set it up here.
All right. We're rolling.
This is the quarter scale replica. It's pretty much in detail, right down to the last spark plug, you might say. It's got dual spark plugs, rollized rockers. I wound my own valves. Everything is pretty much just like the original. It's got aluminum cylinders. Each cylinder has a cast iron sleeve. The cam mechanism inside is exactly like the original. Every part is made just like the original. There's probably close to 5,000 parts if you want to count all, every nut and bolt. And it's...
Well, you made them all, didn't you?
I made them all. It took me about 1,500 hours to build it. Now this is a rotary. Now what a lot of people don't understand what a rotary is, that the crankshaft is this piece back here which bolts right to the aircraft, just like it's bolted to this stand. And when the engine runs, the entire engine revolves, like so. And the crankshaft stays still. And the reason they built an engine like that was, when you build an engine of this design, the pistons don't reciprocate. They merely rotate. Therefore, there was no need to counterbalance a piston with a weight. So you eliminated all your counterbalance weights in the engine, which made the engine lighter. There again, the drawback was that the whole engine had to rotate. But at that period, they were only flying about 60 miles an hour, and they needed that spinning action to cool the engine with air striking each cylinder. Now, I'm wondering if I could...
What's the name of the engine again?
It's called the Bentley BR2. It was designed by W. Bentley, who built the Bentley automobile, which later sold out to Rolls-Royce. And he was the chief engineer on the project, and that's why they named it after him. If I get a little...
Did you make your own spark plugs?
Yeah, I made the spark plugs.
What about the ceramic part? How in the world did you manage that?
The spark plugs are made from a piece of ceramic tubing that's used in the electrical industry, and I use Loctite to hold it to the bodies, which I machined up from regular round bar stock.
Mm-hmm.
There you go. This is one of them. I machined the bodies up in the lathe. This piece of wire comes from an old hair dryer, which is nichrome wire.
I can't see.
You're going to lose the focus if you
yeah.
get too close.
Yeah. Okay, I think we can see now.
Can you see it?
Then I slipped a piece of Teflon tubing over it and turned up a small brass piece and soldered it on the end of the nichrome wire.
Mm-hmm.
But they work pretty good. It's got a quarter 32 thread, and it's pretty close to being quarter scale. It's actually a bit larger than what it should be, but it's a lot easier to make this size. You start to make a spark plug much smaller than that, it becomes very, very troublesome.
A little bit like this.
In fact, making them this size...
There you go.
In fact, making them this size is enough trouble. This is one of the intake valves.
You getting a big picture?
Made out of stainless steel.
Uh-huh.
This is a cylinder head that's machined from the solid. These got quite dirty. I've got them coated with something so they won't rust. Needless to say, all the dust sticks to them. This is an extra head that I made while I was set up the machining procedures. Also got a cylinder here so you can give you an idea what the inside of the engine looks like. This is an extra that I had made. Had a little accident when I first started it. I didn't have enough piston to wall clearance, and I had a seizure take place, and that's where this piston got damaged. But it gives you an idea of what the inside of the engine looks like and how big the pistons are. Each cylinder is made out of aluminum, turned from bar stock, and the cast iron sleeve was turned from a piece of cast iron bar stock, and turned to a very thin dimension and pressed in with a small shoulder. And the cylinder head is held onto it, and seals at this point, held on with the 4 bolts you see right here. Show you the back of the engine. This is what is designed to look like a magneto. In reality, there's contact points in there that trigger this remotely mounted coil which goes through this wire. There are two of them because it's dual ignition. This is an oil pump that runs off of a gear inside here, and it winds up with a 16:1 ratio between the small miniature piston. Is a piston of 1/8 of an inch in diameter with 1/8 of an inch stroke that operates a pump that pumps castor oil into the crankcase to lubricate the main bearings. From there it gets thrown to the outside and lubricates the pistons. And this system is called a loss lubrication system, because what happens to the oil is the fuel enters through the carburetor, which is on the end of the crankshaft. This is the carburetor, which by the way is sitting pretty much between the pilot's legs in the aircraft, because this is the firewall at this point. The pilot would sit about here with this between his legs, and the air and fuel enter into the same crankcase as the oil is in. Now the air and gas mixture goes up through this intake manifold to the intake valve, gets burnt in the combustion chamber, and comes out the exhaust. That's the extent of the exhaust system right there. Now,
Enough to hold the valve.
what happens is, yes, that's exactly what it is. It's a cage just big enough to hold the exhaust valve stem. That's it. Now what happens is, the same oil that lubricates it is impossible to stop it from going through. So what happens is, the oil goes up through the combustion process. Most of it doesn't even burn, gets thrown from the engine. That's why you always saw the pilot wearing these goggles, and when he got down he had oil all over his face, and everybody thinks that that towel, well, that scarf
right,
that they wore was a scarf, but in reality it was a towel to wipe the oil off his face. So this engine uses what they call a loss lubrication system, and it could be pretty messy.
Is it a lot different than mixing the oil and gas?
Yes, because you take a snowmobile or any one of those machines, you would mix the oil and the gas, and the oil that was mixed with the gas that went through the crankcase of a 2-cycle. Now you got to remember, this is 4-cycle, unlike a 2-cycle. A lot of people think if you mix the oil and the gas together, it's automatically a 2-cycle. Well, that's not what determines a 2-cycle and a 4-cycle. This uses castor oil. Now, castor oil will not mix with gasoline. It's not a petroleum-based product. It's derived from the castor bean. So what happens is, the oil goes through the same crankcase as the air and gas, but they never mix. The oil stays all clung to the parts it has to lubricate. Some of it gets carried along with it in small little globlets, and it goes up through the combustion process and thrown from the engine in the same fashion into a mist. And they never really mix. They go through the same engine, but the reason they did that is they didn't want the gasoline washing off the lubricant that was stuck on all the internal parts. I can't say, by mixing it like a 2-stroke, today's 2-strokes, I don't know how well that would work, to be honest with you. I haven't tried it. I've been pleased with the way this works, so that's why I left it. Plus it's the way the original one was, and the intent was to build a replica of the original engine.
And you had a propeller for it too, didn't you?
Yeah, I have a propeller. You still got that in focus?
Yeah.
Yeah, that's focusing.
Why do you have these tipped?
So you can see it. It
Yeah.
disappears when you run it. Maybe safer to have. You see this white line.
Oh,
It
so you
turns so
don't
fast.
put your hand with
Yeah,
it.
it turns so fast you can't see it.
There's almost a full screen spark plug.
That's focused?
Yeah.
Well, what are you doing to get it to focus?
Holding down the macro button and
Oh, you got to hold it.
yeah. And sort of using the zoom as a focus.
Oh, you got to hold it down. That explains it. This is the propeller.
No, it won't focus.
We've had it for a little while. Oh, look at that. It pushes those little things back.
Well, this is a washer. This is supposed to come off, and this goes on, and all these bolts go through this.
Oh,
And that's how it's held
so
on.
the washer's just there to keep everything intact.
Well, it's a drive washer. The washer is splined to the shaft here. So it becomes a drive washer just like the back one. So it drives through these bolts. The entire torque of the engine is putting power. Now you got to remember that this here is quarter scale, and it measures 26 and something like 13/16. The original one was over 9 feet long. But when they'd start this thing, they would have to grab that propeller and the entire engine and spin the whole business. It's quite a feat to start this thing. In fact, this one was one of the biggest rotaries that were built, and it was started with what they call a Huck starter. It was a big tripod mounted on the front of a truck with a belt going up to it, and they'd come in with a long shaft and connect here and spin the engine over from another engine, because it was a tough one to start.
You said it used gasoline for fuel?
Yep, it runs on gasoline, lubricated by castor oil. The tank here has a baffle in it, and this is a castor oil tank, and this here, from here to here, is the gasoline. This is by shut-off. This is a fuel mixture, and this is the slide-type carburetor. I could put a coil.
So the pilot could move it.
He could throttle this one. The early ones were not throttleable. They used to control the speed of the engine by killing the ignition. This particular one, yeah, when they would start it up, it was going wide open. So if they were going too fast, they would push the button and it would shut the motor off. And because of its rotating mass, it's its own giant flywheel, it would coast for 30 seconds. Then before it would completely stop, they would let go, so it would pick up a little more speed, then they'd kill it again. That's how they control the speed. When they come in for a landing,
Chancy, isn't it?
well, that's when they used to fly by the seat of their pants. They would actually come in for a landing, and to slow up the airspeed, they would keep killing the engine until they got the speed they wanted, and then they'd set it down. Then before it would stall, they would blip it, and then make a turn, and then taxi down the runway.
What kind of wood do you use for the propeller?
Poplar.
It's lightweight, isn't it?
Yeah, I use poplar because it's easy to carve. It's 6 pieces of 1/4-inch poplar all glued together. And you can see where it's been glued here with epoxy type glue. And that's what gives it this little line right here. That's each piece. See?
Wow.
Had to make the templates to carve it every 2 inches. There was a template. It bolts to like a 2x4 or a known surface, and you work from that surface. Now there's a set of templates for this side, and there's also a set of templates for this side. See, the propeller has an airfoil to it. See the curve? So what it's doing is, as it's rotating, what it's doing is it's creating a low pressure area right here, which is actually pulling this way. Atmospheric pressure is pushing here because you've lowered the pressure by creating an airfoil here, just like a wing on an airplane.
A spinning wing.
Yep. But that's the propeller. Yeah.
This Roddy?
Oh yeah?
Mm-hmm.
Well, I'm sure he'll be. You can show him this footage here, and he'll probably be able to relate to it.
Yeah, plus he works on small engines all the time, so he's got a good concept of how they work. So what are you going to stimulate here? You want to have a bench?
Okay.
Okay. There's a different height one over here. So you're going to use a current to do what?
For the spark.
For the spark?
This is some remotely mounted coils. I haven't mastered the art of rewinding a 1/4 scale coil,
That ought to be fun.
although some guys have.
Coil wire's pretty fine, full size.
So you had to machine tools to make some of these parts, didn't you?
I have machined many tools. I've got a box over there under the bench. I could spend 2-3 hours showing you how I made them and what they do. And
I bet it took a good bit of patience to put this together.
Well, it took about 1,500 hours over a period of 2 years.
Mm-hmm.
So I haven't started this.
A full work year is 2,000 hours. It's a lot of spare time.
Yeah.
Some weeks I worked more on this than I did at work. If I work 40 hours at work, I'd work 35 and 40 here.
Yeah.
I'd come
you
out
have
here
to.
in the evening at 6 o'clock, and I'd work till 11, 11:30. 5 days a week. Then on Saturday, I'd be out here for 18 hours, 16 hours, and then Sunday, the same thing. So, I was having fun.
So if anybody needed to talk to you, they had to come out to the garage, huh?
Yeah. Oh, yeah. Well, you get on a roll. You ever been on a roll
Oh,
with
sure.
something and you get going good?
Uh-huh.
And you just want to keep going. Yeah, this fuel. You just ought to run.
How are you going to spin it with no prop?
I just push the engine.
Oh, yeah.
It doesn't need a prop because there's so much flywheel action. Throw the ignition on.
I do like this. Ah.
A little bit.
Like I say, it throws oil, and what I had done, I washed it down before I put it away, and I coat it with penetrating oil so it doesn't rust. And so, needless to say, when you start it, the first thing it does is throw everything off of
Spews
it.
it everywhere.
Yeah. But it came alive pretty easy.
Yeah,
Yeah.
it did. It sure did. And it was smooth.
Well, it's very smooth because nothing in the engine reciprocates.
What was the size of the original engine, Roll?
It was 9-cylinder. It was 25,000 cc's, which just
Wait,
translates
25,000?
25,000 cc's. It translates to about 1,500 cubic inches. Now just picture 3 454 Chevys.
Yeah.
Right? That's basically how big the engine was.
1020 compact cars.
So it gives you an idea how big the original one was. It developed 235 horsepower, which is not a lot with today's standards on horsepower, but back then that was a lot of power. When you stop and think that the average aircraft engine had somewhere in the vicinity of 35, 40 horsepower. This is 235. I mean, that's like the relationship is like today's F-16, right?
Wow, yeah.
So, in any case, this one is being quarter scale, scales down to 347 cc's. Now you say, well, geez, you stop and think about it. Take a 350 Honda, right, and you can see how much smaller this engine is because it utilizes one crankshaft journal because it has a master rod with a whole series of rods tying into it. Unlike a 2-cylinder or 4-cylinder engine would have to have a crank and a journal for each piston, makes the engine longer. This engine is much more compact. So, you know, you stop and think 350 cc out of an engine this big, that's pretty good too. So,
And this one's portable.
well, yeah, this one's portable, all right. I knew it was going to throw oil. Most of it is thrown down and out. That's the slipstream throws it this way. That's why I think most of it went that way.
I'm glad it wasn't on your ceiling.
Well, it probably is, because the last time I ran it, I did get oil up there.
Unless that person is well versed in how machines generate.
Everything I own is covered with castor oil.
Castor oil, that's what they used to give the kids.
That's exactly what it is.
Like in Spanky and our gang.
Yeah.
Remember there was a kid always, the alarm clock would go off and the kid had to use castor oil?
Well, what it did was, those are two planes. That's a slide type carburetor with a
Slide
tapered
carburetor.
needle. Very much like a Walbro or a SU carburetor. Something you'd see maybe on a motorcycle,
Yeah, snowmobiles.
snowmobile, yeah. The principle is...
Good.
See if you can point.
Okay, well, what I could do is shut it off here. I can stop it, I can switch. All right, what it is, this is the center for the connecting rods, like I spoke of. All right, this would be the crank pin. This is called a master rod, this particular one, which is number 1, which is fixed solid to this round ring. All the others come in here and tie in with a small wrist pin. And they're allowed to flex at this point. And they're also allowed to flex here. Now the way this works is, this being offset, as you can see the piston is at the top of the cylinder when it's at the top, and at the bottom when it's at the bottom of the cylinder. Compression takes place here, and you'll notice that every other cylinder fires. That's the reason for the odd number of cylinders. There's 9 in this engine. But what happens is, being a 4-cycle, it needs 2 complete revolutions of the engine to go through all 4 cycles. The intake stroke, the compression stroke, the power stroke, and the exhaust stroke. Now this is accomplished in this engine just like it would be in most any other engine. But every other cylinder, while this cylinder here is on the power stroke, the one adjacent to it is on the exhaust intake stroke. And what it does is, if you fire every other cylinder, being an odd number, 2 revolutions, you've fired them all. Now, down here, you have the cam mechanism, which is a little more complicated. This would be virtually impossible to explain without showing you how it works.
Can you make it run slower at all?
Well, I can do it this way. This is the lobe. This particular thing is made double scale. This would actually be half this size, mounted in the front. Now there are 2 of these. That's the reason for the offset in the engine here. The ones on the outer side operate the exhaust valve, and the ones on the inner side operate the intake valve. Now this particular piece here is just a slice of one of these. There are 2 stacked on top of each other, timed in such a way that they open the valve at the correct time. Now the way this works is, unlike a conventional camshaft, it has a gear that operates inside of another gear. Now this gear has 16 teeth, this gear has 18 teeth. That means every revolution of this engine, this cam moves ahead by 2 teeth. Now this has 4 lobes on the gear. Now what happens is, this lobe operates this lifter, which is opening, you can see the space here, it's opening the valve. This is connected to the push rod, which in turn is connected to the valve. Now, as this rotates, you can see what happens here. The valve closes at the bottom. Now we're going to come up with this cylinder, we're going to go to the compression stroke, power stroke. So on the power stroke, the engine, this valve has to stay closed. So at this revolution, it missed, there's no lobe opposite this particular one, so the valve stayed closed. Now, the next revolution of the engine, the valve is going to have to operate because its turn for the intake exhaust stroke takes place. Now this lobe moves over to operate this valve. The last time it was operated by this lobe. But meanwhile, it's operating a lobe or a lifter or a valve in another portion of the engine. There again, as you can see, this one would be on the intake exhaust stroke. The two cylinders adjacent to it are on their power stroke. Every other cylinder is in an opposite phase cycle. So it takes 8 revolutions of the engine before the same lobe comes back to operate the same valve. Meanwhile, it's operating another valve in the engine, which is very different than a conventional camshaft. A camshaft has a lobe which operates the same valve over and over and over, whereas this one is actually moving around or dancing around in the engine, operating various lobes. But the whole thing comes together and it works.
Awesome.
The lights depict the firing order. Fires at the top, power stroke down, exhaust stroke pushes everything out, sucks in a new charge, compresses it again, fires. Did you follow that?
Yeah.
Yeah, is he holding his hand in front of it so you can't see?
No.
No?
Yeah, we'll do another one here. We'll start with the intake. Intake stroke, sucks in a charge, compresses the charge, fires it. The explosion pushes it down, it pushes the old gas out, sucks in a new charge, pushes it out, fires it. Pushes the old charge out. Now the phase is opposite with the adjacent cylinders. That's why you see every other cylinder is firing.
But in 2 revolutions, it's back to
Back to where it
one.
was, yeah. Just like a regular engine with a the 4-cycle principle is the same. The thing that's different is the fact that it's a rotary and the engine is
designed it?
revolving.
Again, who's?
It's the
Bentley?
Bentley, W. Bentley, William Bentley, that designed the Bentley automobile. He was a young engineer working for Vickers of England at the time, which was about 1915. And this particular project, he was the chief engineer on the project, so what he did, they named the particular engine after him. He's not credited for everything on this engine. He's credited for using aluminum cylinders and aluminum pistons, because prior to that, nobody was using aluminum on pistons and cylinders, and they all had overheating problems. So he knew that the pistons, because he was involved at auto racing, he knew that the aluminum would dissipate heat much better and it was much lighter. So he chose to use it, and it was very successful. Shortly after that, most everything was made out of aluminum. He later went on to design and build a Bentley automobile, which was sold out to Rolls-Royce, and everybody's familiar with the Bentley when you talk about the Bentley. But this was earlier in his years. This particular engine was a spin-off from a French Clige. It's if you look at a Clige, it's very similar to this engine. In fact, this mechanism he thought was so good, he didn't change it one bit. He used this identical arrangement. This particular, the engine was quite different up in here, the way that the valves and the intake manifold ran. But it was the last of the rotaries. Shortly after this, they became obsolete because they could build the engine so light. There was no need, and they were able to cool it because they were using aluminum. There was no need to spin the engine. So now they started to produce radial engines, which is an engine that sits stationary, and this crank pin revolves around like this and causes the pistons to go back and forth in the cylinder, which is the way all radial, or I should say, yeah, radial engines are built today. But this here, you got to remember, is a rotary, and being rotary, the entire engine rotates.
What's the advantage of the radial over the rotary?
This suffered from 2 major problems. One was the lubrication. If the engine rotates, you do not have an up and a down or a left and a right to the engine. It's completely symmetrical. So there's no place for the oil to gather so that you can repump it and use it in the engine. That's why it used the lost lubrication system. The lost lubrication system would literally sling the oil due to centrifugal force into the cylinders to lubricate them. There's a problem getting the fuel to it. They had to feed it in through the crankcase, which caused the two to mix and get thrown from the engine. So that was a big problem. The other problem was the gyroscopic kick. The pilots called it that. It's actually the gyroscopic effect or the flywheel effect of the engine. Now you've got an engine that weighs about, let's say, 500 pounds, which is probably as much as the entire airplane weighed. So when you would accelerate the engine, the torque from the engine wanted to spin the plane in the opposite direction. Now, unless you counteracted with a force off of the elevators to counteract this force, it would literally spin the airplane around. And it was a very difficult plane to fly till you learned how to coordinate the throttle and the rudder. Because every time you would throttle it up, it wanted to spin the plane. Very much like a helicopter. Today's helicopters all work in the same fashion. When you accelerate a helicopter, it wants to, you're applying as much torque to the helicopter, so the entire helicopter wants to spin the other way. So that's why they put a tail on it with a spinning propeller, and that propeller has to vary the pitch of that propeller either to take a big bite or a little bite of air in order to compensate for the torque that's being applied to the helicopter. It all sounds easy, but to coordinate the two was quite difficult. The pilot had to feel the plane and compensate, and they lost a lot of pilots on takeoff. He would accelerate the thing, and the torque would be applied to the plane who wanted to lift the tail, and they would bring the tail right up and crash the plane. So you got to remember 1915, you know, and there were other rotaries built prior to this. The French were great for building rotaries. They had the Gnome, and another one was the, let's see, the Gnome, and the little Clige was another one. Mono Super Pop. That was one that used a valve in the top of the piston head, and the fuel was right in the crankcase, so rather than manifolding it up through the outside to a separate valve, they ran it in through a poppet valve right in the top of the head. Not quite as efficient as this engine, but it did work.
Get castor oil in your goggles, Rollie.
Yeah, I know it. Got it everywhere.
That's a great model.
The buildings are beautiful and large and orderly place with comely streets whose continual enlargement bespeaks a sumptuous city. These words were written by London Sea Captain Edward Johnson. The year was 1654.
How'd you get wet? For Roland.
This particular engine is a hot air engine. This was designed by Andy Ross. What it is, it's a hot air engine. Works by alternately heating and cooling a working gas within the cylinder, causing an expansion and a contraction, driving a piston back and forth. And this is a burner which heats this portion of the cylinder, which is the hot end. This particular piston on this side is the cold end of the cylinder. What it does is it alternately takes the working gas, in this case it's just air, many gases can be used, but it pumps the air by displacing it with the displacer piston, forcing it down to the colder cylinder, and in going to the colder cylinder the gas gets cooled, causing it to shrink. So now inside is a low pressure area and the pistons actually get sucked up, and In doing so, it's timed in such a way that the pistons cause the same gas to get reheated on the hot end of the cylinder, therefore pushing the piston back down. And this is timed with a crankshaft and causes the engine to rotate. So there are no valves, no intake, no exhaust, there's no spark plugs. All you need is heat on a hot, all you have to do is heat this outside surface area. And this is a burner which runs off propane. And propane heats this cylinder, and the engine fires off. This particular engine will run at 2,500 RPMs. I had the occasion to go to Indianapolis, Indiana, and meet with this fellow who designed this particular engine. We went out to eat in a restaurant, and we spent 3 hours at the restaurant with a notepad exchanging notes with all kinds of different engines. Let's see if I can get a propane torch, because my burner is not working as well as I'd like. So I could heat this with a propane tank and now the engine is running on the heat that I just stored into the hot end of the cylinder. This engine will turn up about 2,800 RPMs. It's water cooled. The water goes in here and out here. I'm not running water on it right now, but just for a little short demonstration you can get an idea of how it works. But that's probably turning 1,200 RPMs right there. When everything is right, I've had it up to 2,700 RPMs. By alternately heating and cooling a gas, 25, 30 times a second. You wouldn't think, everybody thinks a watch pot doesn't boil, but you can actually heat and cool a gas that fast, causing it to drive the piston, providing it's timed correctly. It's slowing down because it's pumping the heat out of this into the cooling system over here. Now there's this few versions of this. I've seen somebody put a parabolic reflector in here with the focal point being the hot end of the cylinder, and they just aim it at the sun and give it a kick and you've got instant solar power. Ford Motor Company back in the 70s experimented with this engine. It's called a Stirling cycle engine, or a hot air engine, because it's a multi-fueler. Anything that'll burn and make heat will operate it. It's an external combustion engine, and they felt for emissions it probably would be better because you could design a burner with a very hot surface area so that you burn the gases very completely. And they had an engine putting out as much horsepower as it was cubic inches. But every time they make a stride with some type of engine, the internal combustion engine seems to take another step and stay ahead of it. But it's kind of a unique little engine. In fact, there is a company, Philips company in Holland. They manufacture an engine that runs a generator. Very quiet because you have no intake or exhaust, and it runs a small generator, and I think it runs on propane. They use them in campers. But this shows the basic principle. And as far as efficiency, is probably the same as burning gasoline in an internal combustion engine. Some people claim better, but in any case,
What's this over here?
that's a water pump. I run a little belt, which is an O-ring around here, and this pumps water through the engine to a big tank where the heat is dissipated. So you're actually pumping the heat from here through the engine, making mechanical power from it, and then losing it to the atmosphere through water.
Would you get better performance with a different gas?
Like I say, you can burn anything. The early versions of this is the engine, meaning the principle, not this engine, and not this design of the engine, but the principle of the engine was designed in, I'm trying to think, 1760 by Robert Stirling. And they used it to pump water out of the mines. And he developed the system. They would burn coal, which would generate heat on the hot end of the cylinder, and it would run a pump to pump the water out of the mines, and they would pump the water around the coal end of the cylinder and pump the heat out of the mine into the that was put into the water. So the principle is not new.
But I mean the gas that's like the air, the working gas.
Oh, okay. The working gas, they use a light gas, like hydrogen is a good gas, or helium, because being lighter, it absorbs the heat quicker and gives it off quicker, and the efficiency is better. Now, in order to get more power out of the engine, what they've done is they've increased the amount of air or gas in with the cylinders by compressing it. Now, if you compress the air, you double the atmosphere. You've doubled the amount of molecules that are in that working gas. So you've doubled the amount of heat that it can absorb. So what they've done is some of these engines have had internal crankcase pressures as high as 1,800 pounds. It's a form of supercharging, I would guess. But it really works. Now the engine has the ability to absorb a lot of heat because there's a lot of molecules inside in that compressed gas. But you run into problems. Hydrogen is a good gas, but it's flammable. And the fact that it's under 1,800 pounds of pressure, that alone, with any lubricant in the crankcase, could explode, very much like a diesel. Fuel oil will explode due to the pressure on the fuel. You run the risk of having an explosion with an engine like that. But I've never really seen this, well, I can't say in a practical form. I've seen them in practical engines. The military used them during World War II to run generators. They couldn't afford to run an internal combustion engine to run a generator out in the field to run radio gear, because the spark from the engine would interfere with the radios. So they used a hot air engine to run a generator to make power, to charge the batteries, to run the radios. So they were used in nothing in a big sense. I think the biggest hot air engine that was ever built was a 50 horsepower engine, and it was gigantic. Everybody's heard of the Fulton Folly, which was they thought was a steam engine. In reality, it was 10 foot in diameter pistons driving the paddle wheels of the boat. And the reason it didn't work was it really wasn't a steam engine. What he was doing was he was putting hot air in the cylinder or steam, allowing it to cool, and it would create a vacuum, and atmospheric pressure would push on that large area of piston and drive the crankshaft. And being such a big diameter, it couldn't cool the gases towards the center of the piston effectively. And it turned out that making something larger wasn't necessarily better. And it turned out everybody's heard of Fulton's folly, and it was actually this principle applied to a big engine, which didn't work.
This is an interesting looking one.
Okay, well that again. What this is, most steam engines have a piston in them that's double acting, which means that the working gas pushes the piston this way, and also pushes it back. Now, to connect that piston, which is in the middle of the cylinder, has to be connected to a rod, and this is the rod right here. Now, that rod has to be supported at this point so that it doesn't bend. So most of them have a sliding guide. Well, this particular approach is a little different. The design of these links and the length of these links all are of a correct length so that the motion of this particular pin remains parallel to this shaft, therefore supporting it. If you watch this, when I move it slow, you'll see that this point is swinging an arc from here. This point here is swinging an arc from here. But this arc and this arc cancel at that arc, and this particular becomes a straight line, this particular pin movement. So you have this one swinging an arc, this one swinging an arc, but because of where the pivot points are located, this particular pin moves in a straight line. And everything else is pretty much like a steam engine, like that steam engine that I showed you earlier. It's got an eccentric that runs the valves on this side, and it runs.
So where's
that
the
fashion.
inlet for the steam? Oh, okay.
Okay, it goes in there and out here.
Out there.
There again, I've run these on compressed air. I started a boiler, but I haven't finished it. A miniature boiler that would run on either gas or some type of mineral spirits to make just a little bit
When
of
this
steam.
is running, is it uneven
Yep.
sound?
Oh,
Or
yeah.
even- Where's the one that spitter sputters? Sounds like it's... Do you actually make the neural nuts?
Oh
too?
yeah. Yeah. The coils are remotely mounted.
So does this have spark plugs?
One.
Oh,
Actually, the spark plug is out of scale. What I should do is put one of my miniature ones in it.
okay. Look at how many connections he's got going here.
That one. Now, let's see. Go.
Do you have a good angle on that, Sean?
No.
Yeah. Let's move the other one out of the way so we can... There you go. I'll put it back. Oops. What's the fuel here?
Gasoline.
Gasoline.
This is called a hit and miss engine, which was typical of a lot of farm engines. This is made with no castings. It's made out of a couple pieces of angle iron, some blocks of steel, a cylinder that was pressed into the block, and the valving is made from, and the carburetor here is made from various brass pieces. These flywheels were made from some old slugs that were cut out or left over from a particular job.
doesn't burn very cleanly, does it?
No. It'll clean up a little here once it gets warmed up.
And this hit and miss sound is normal for it.
Yeah. What it does is there is no throttle in the carburetor to control the speed of the engine. The speed of the engine is controlled by holding the exhaust valve open. Got to get a little heat in it before it goes good. I start this thing up at the engine shows and it'll run all afternoon.
Well, I can tell when it's firing, but what are the other weird sounds that it's making? That slurping noise.
Well, when the valve stays open, the piston continues to run, so it sucks air in the exhaust and then back out the exhaust. Then back in the exhaust and back out the exhaust.
Ah.
So now when it's allowed to cycle, then it fires. The intake valve gets sucked open. Do you see it twitch right here?
Yep.
What I gotta do is get a little oil. I'm flooded, and it's washed all the oil off the cylinder. Get some oil in it.
You know right what to do to make it go again.
What we've got, we're so flooded here. The gasoline running out of the. And I get some dirt stuck under the exhaust valve. I can hear it leaking. Which compounds.
I think this is one of the most interesting ones because of the gurgling noises it makes and the uneven firing.
Yep. Now, if I keep the load on the engine slower, the governor stays in, and what it does is it fires more frequently. When these governor weights sling out, this mechanism causes the exhaust valve rocker to become disengaged from the cam, so it prevents the engine from cycling through its normal cycle.
Did you tell us who designed this engine?
This particular engine? Well, okay, this one was designed by a fellow named Philip Duclos. He did an article in one of my magazines, and I built it from his article. And it looks very much like what they call a Witt headless. A Witt was an engine built at the turn of the century, and it has no cylinder head to speak of because the cylinder is incorporated into the casting, but there's no head on it per se that bolts on like most engines. So that's why they called it a Witt headless, and this is made very similar to that. Yeah, it's going pretty good now.
Yeah.
The points are over here, which causes the spark to come at the proper time, and it's made from an old hacksaw blade. These are made from a couple of pieces of angle iron bolted to a flat piece of steel. Then I filled it in to make it look like a little casting. You can see the